Getting some glare there. Okay. Well, So down there you can see that probably much better. So that up there says principal component analysis. Hopefully you all can hear me. Can somebody give me some feedback on the live channel just so I know? Oh, yes, there we go. Well, if you raise the laptop, that's a really good idea. You're smart. You must go to Georgia Tech. Excellent. Thanks for the suggestion to get rid of the glare. I think you guys are seeing this in the right direction. It looks mirrored to me, but I think that's okay for what we're doing. I think it looks in the right direction for you. Can you read principal component analysis there? Can you read this? Let's make sure that YouTube has not messed it up. So while I'm waiting for feedback on readability, let's get to the Piazza questions. A little dark and thick marker would be, yeah, this is the darkest and thickest I've got. Let's see what this is. This looks like it's not dry erase. Oh, yeah, it is. Kind of. Oops, I think that's actually not dry erase. That's a flip chart marker. Yeah, let's not do that. That seems like a bad idea. Okay. That's coming across pretty close, I think. Okay. So let's get started on the questions. Now that we have stuff set up. First one, happy Halloween, brains, wonderful. Yep, so we have no questions there. So do we have any questions on the live chat here? Because if not, I will get started with the with a little lecture. Let me move this closer. Now we got rid of the glare. I think we can actually do a decent job here. Look at that. Okay. So one thing that's missing in your lectures is a technique called principal component analysis. It goes by several different names. One of them is singular value decomposition. Or if you look at my own papers, there's something called eigenfaces that was done back around the early 90s. And it's like, if you look at Google Scholar, it's probably my most referenced paper. That was primarily done by Matthew Turk and my advisor, Alex Pentland. But it's going to be the basis of the lecture today. And it kind of shows you how you take something that has a high number of dimensions and reduce it down to something that's actually manageable when you're trying to do pattern recognition on it. So this is kind of this is another way to deal with feature selection. You've already had decision trees where it uses information game to figure out which feature you're going to use to discriminate different classes, and you can have hundreds of features, and decision trees will try to figure out the best feature for it. Boosting does the same sort of thing. You've seen that lecture by now. Boosting looks to see which collection of features might be best. And you really want to use these techniques when you have a lot of features and you don't know which ones are going to be the best. Feature selection is one of the key problems in machine learning, pattern recognition in general. If you can find a good feature, the problem becomes easy. But if you can't find a good feature, the problem is hard, or at least some combination of features. One way you can actually get to this is looking at which features most represent the data, or which features most discriminate the data. Now, principal component analysis does the former. It says basically which features best describe the data. Now, let's talk about that for a second. Suppose I have, let's see if I can get red here. So red and blue would be best. Let's see how my red dot looks. Okay, so I have, here we go. I have my axes. So this is my x-axis. This is my y-axis. Then we have, a video game distractor here. For those of you with short attention spans, you can just watch the cord. Apparently, this is going to be a problem, but I don't see any way to solve it, so we'll just keep on going. So I have the x and y axis, and I have lots of data. So here's some of my data. Here's some more of my data. Right? And so I have about 2 classes in the data. Right? And if I was going to put a bounding ellipse around the data, it would look something like this. Okay, now back when you're doing linear algebra, you had the ability to do Gaussian reduction and find the eigenvectors and eigenvalues of a matrix. And one of the things you can do is say, okay, if I have a lot of data, if I have a lot of 2D data points here, I just put them in a big matrix, we know there's only 2 independent dimensions there, right? But if I took all these data points, I put them out there, I did the eigenvectors of this thing, I could actually figure out which axis most represents this data. So let me do that graphically for you. If I was going to take some component of this data set and say that component most represents this data set, it would be the mean. It would be this point right here, right? That mean right there, because it is in the center of all the data. But now if I do the next most important dimension for this, it's not going to be the x or y dimension. It's going to be the major axis of the ellipse. And when you're doing eigenvector and eigenvalue analysis, the first eigenvector, we'll call it lambda 1, because that's what most linear algebra textbooks call it. That is the first eigenvector. And matter of fact, the first eigenvalue would be the length of this right here. Right? And then the second eigenvector has to be perpendicular to the first. And it's going to be the minor axis of this ellipse. Now, I said, and this is an important concept, I said that besides the mean, the first eigenvector is kind of the thing that is the most salient piece of information on for that data. But more specifically, the projection of a given data point onto the eigenvector is the most important thing to send. So imagine that I am sending an image to the moon, or better yet, imagine that I'm sending video of President Johnson, I believe it was, to the moon to talk to the Apollo 11 astronauts. We're talking about 1969 technology here. How can I send a video image to the moon? Well, if I actually have a digital system, what I can do is store a lot of information ahead of time and actually send over images based off that data. So what I'm going to do is I'm going to take lots of pictures of President Johnson and of the NASA director and anybody else who wants to talk to the astronauts. I'm going to send those, I'm going to do this principal component analysis on it, which is basically finding, first of all, find the mean of those images, and then find the axes that most describe those images, and I'm going to send those over first. To make this stuff simpler, what we're going to do is we're going to say, okay, we're talking about images in a little bit, but we're going to make it simple. We're just going to send 2D data points over. So I want to send that over in the least number of bits possible. So let's say I want to send over this data point right here. We'll make it this one here. Right? Hopefully you guys can see that. Yes, you can see that. Okay. So normally what I would do is I'd send over the x coordinate and the y coordinate. But that's an inefficient use of bits, right? I don't have any data in these white spots. In fact, I don't have anything that's in the minus sign of the x or y. So I don't need the bit that says minus sign. So I could throw that away. But even better yet, if I actually recenter my origin to the mean of this data, I can save a lot of bits. I don't have to span a large range. All I got to do is span the range of the data in this ellipse, and I can specify at the precision I want to do it. So you can imagine, like in the extreme case, if my data point is like way off, the board here, in order to have enough bits to describe everything well, I have to have a lot of bits, like say 32 bits of precision to really get a fine, detailed location of the data in this thing, because I'm representing all this white space. But instead, if I say, okay, I'm going to move my origin from here to here, right? Now what I got to do is say how far the data is from the origin. And in particular, what I can do is I can say how far is that data point from the medium, the mean along the major axis, along the first eigenvector. So what I'm doing is I'm going to actually send over, so what I send up with the astronauts is the mean x and y, and then I send over the x and y coordinate, so basically this point here, of the eigenvector, right? Of the first eigenvector and of the second eigenvector. So that's what the astronauts go up with. And now as I'm sending data over, what I'm doing to specify this data point is I'm saying this is basically minus, say, 1.1 standard deviations, so 1.1 sigma along the first eigenvector. So that's like my x coordinate from before, but that's my first eigenvector coordinate. So I am 1.1 standard deviations along, minus 1.1 standard deviations from the mean along the first eigenvector. And on the second eigenvector, I am, let's see here, I am this. And so I'm doing this little spot. So I am, say, I don't know, plus 0.5 standard deviations along the minor axis, or the second eigenvector. And so I can actually encode, if I'm just encoding these projection values, I can encode this very efficiently, because when I send this back up to the astronauts, I take the means, I just add the standard deviations from that, right? And that way I can transmit all the data in this data point for any given data point. I can transmit it extremely efficiently up to the moon. And depending on the amount of precision I need, if I'm trying to do this in a good job for something like this, I might need only 8 bits for the first eigenvector, and maybe even 6 bits for the second eigenvector, right? So I can do this very efficiently. Every point I can send up in 14 bits. That's very efficient, as opposed to, say, the 32 bits for a y and 30 bits for x that I was starting with. Okay, so what does this have to do with faces? Well, let me show you an idea about the how we actually take a face and actually do a very similar job here. So suppose I have pictures of President Johnson. He is a very sober-looking man, kind of squarish head, if I remember right. So that's my first picture of Johnson. And here's the second picture of Johnson, where he's cracking a smile now. And my third picture of President Johnson, I don't know. Oops, you can tell I didn't go to art school. He's now angry for some reason. I don't know. And so that's the president. And then I have pictures of the NASA director. I don't remember who the NASA director was back then, but we'll call her Shirley. Here's my first picture of Shirley. And my second picture of Shirley. Her looking cross. And that's probably a good Halloween face there. And then Nancy looking happy, right? Suppose I have like 20 different people here I'm planning to actually send on my video conference, and I take, say, 100 images of them. So that means I have a database of 2,000 images, right? But I'm not going to be able to send much data up, so I'm going to reduce these things down to just a 32 by 32 pixel image. So here is my picture of Johnson that I'm sending up. And I'm going to break that down into 32 by 32 pixels, which is approximately equal to about 1,000 pixels. But what I'm going to do is I'm going to read them off serially, right, from left to right, top to bottom. And so I'm going to get this matrix of 1,000 pixels for the first image of President Johnson, 1,000 pixels for the second image of President Johnson, and then I go here, and then it's the 1,000 pixels for the first image of the NASA director, the second image of the NASA director, their 1,000 pixels, etc., going out to the 20th person. And so I have 1,000 pixels down, let's say 2,000 images here. Now what we got is, you can still say that, very good. So what we got is a matrix that is 2,000 by 1,000. But from linear algebra, we know that there can only be 1,000 independent dimensions here, right? So I take the eigenvectors of this, and by the way, there's an efficient way of doing this. If you actually take, if you do this and do the transpose for making your matrix going, you only have to do the 1,000 by 1,000. That's a key insight on the Eigenfaces paper. If you go look this up on the web, so for eigenfaces, you'll find this. You end up with a 1,000 by 1,000 matrix. You do the principal component analysis on it, or support or singular value decomposition, whatever you want to call this, eigenx, and you get a series of eigenvectors. And those eigenvectors are just like the two-dimensional vectors, but now it's in a 1,000-dimensional space, right? And if you look at the images, the first image, if you go. Actually, you know what we can do here? Can I do this? Can I actually share my screen? Because that'd be useful. Okay, for those of you interested in this, go to Google Images right now and type in eigenfaces. E-I-G-N. Let's do this. Let's do this properly. So type in eigenfaces. E-I-G-N-F-A-C-E-S into Google Images, and you will find lots of images of different sets of eigenvectors. And the first one you see is basically the mean. And the mean image kind of looks like this androgynous washed out face with the noses and the eyes up here and the mouth, and some of the other stuff kind of gets washed out. It kind of looks like this androgynous angel, right? But the next vector sort of looks like, depending on the set of eigenvectors you have, it kind of looks like this thing where it's encoding the size of the face. So it's actually encoding the variance of the in that 2,000 image database. So a lot of that's going to be the width of the face, and then the next eigenvector, it might be like how much hair you have, right? And so you see these different features, and when you get to the last eigenvectors, it basically is picking up the static in the scene. Right, it's very high frequency stuff. So the first, say, 20 eigenvectors are actually sufficient to do a good reconstruction. So this is what I'm saying. If I was saying that data point off the first time, the first thing is its distance along the principal component, the first eigenvector. If I just use that to reconstruct this data point, just this projection of this eigenvector, I'd get this, this spot here, which is very close to the point I'm trying to send off. And so it'd be very easy to only send the first projection off and get a decent reconstruction. To get the perfect reconstruction, I send the second thing. Now imagine I had a thousand dimensional thing here for these eigenvectors. For these images, and I take, I have Johnson getting ready to congratulate the astronauts, and I have some new face of his, right? And suppose it's like his canonical happy face. I project it down onto these eigenvectors, and since it's going to be pretty close to some of his training data set, it's going to be something like this, where all I need is, like, say, the first 20 or even maybe the first 100 projection values to reconstruct the image. Now let me be very specific about this. What I'm going to do is I'm going to take this image, I'm going to take it and break it up into 32 by 32, just like the other ones, right? I'm going to take this vector and I'm going to do the dot product with the first eigenvector. That gives me the projection value. We'll call that P1. And then I'm going to take the second eigenvector. I'm going to project that image onto this one. I'm going to get P2. On down, and suppose I do this, suppose I do the first 100 eigenvectors projections, right? Now, in theory, I should do all 1,000, and I get perfect reconstruction if it was an image in trained database. But what I'm doing here is just trying to get a good enough reconstruction so the astronauts can see who it is and see well, at least the first image of the video. So how I do is, for the reconstructed image, I take the mean plus the first projection times the first eigenvector, which I already set up with the moonshot, plus the projection value, P2, times the second eigenvector, plus P3 times the third eigenvector, plus the P100 times the 100th eigenvector. And it turns out that I get a pretty good reconstruction this way. And then we'd ask what this has to do with machine learning, but we'll get there in a second. What I'm doing right now is showing you how to send data over a very thin pipe, a very, very slow network connection, and do a very good job of it. So this is kind of like, you've ever seen a progressive JPEG, where you go to a website and it loads in like sort of this blocky image and then refines it over time. What it's doing there is actually really doing these blocks and doing a discrete cosine transform and filling stuff in over time. This is a more efficient way of doing the same sort of progressive JPEG. But what we're doing here is using our trained database of all the images we ever want to send, getting the training up for that particular data set, and then just sending the projections over. And this is how I can do the reconstruction. Now, what's interesting here, when you do this reconstruction, is suppose I get an image that I've never had before. And suppose we're giving, suppose the Sally, our NASA director, decides this is Halloween, that she's going to wear a mask, wear a Lone Ranger mask here, to send up as the first image from her to the astronauts. Well, because she didn't wear the Lone Ranger mask in any of her images, when I project her down these eigenvectors and I reconstruct her, it will magically take the mask away. Because it doesn't have the data to actually send that mask, which is really good if you're trying to use bank video and reconstruct the image of the bank robber. Right? So now I can take the security video of the image of the person who robbed the bank and they're wearing a mask, and I can take off that mask, sort of using the other features of the faces. And I have a big enough database of enough people, it'll actually do a surprisingly good job, because looking at things like eye color and skin tone and face shape and all this type of stuff. If you represent all the phenotypes of humans, in the large database and do this reconstruction, it'll actually do a pretty decent job of trying to remove the stuff that's not there. The first time I actually ran into this, I was actually using the face database to reconstruct people, and I accidentally put in a face that had the eyes closed like this. And when I got the reconstruction back, the eyes were open. I was like, oh, that's creepy. And so we started playing around with just taking out different chunks of the faces and reconstructing it. I was doing a pretty good job. And this was on a 8,000 face database with about 3,000 different people in it. And that was enough variety that given somebody's face with a bit of it erased, I could actually reconstruct it pretty well. Now, with eigenfaces, one of the things you got to worry about is actually getting the face aligned properly. It's got to be about the right size, and most importantly, you got to get the eyes lined up and the face oriented right, so you get good reconstruction. Otherwise, it's going to look, kind of blocky and blurry. So that's the big thing with the eigenface technique for reconstruction. Now, one of the other things I can do then is I can start doing recognition. So suppose I have an image. Where's my Johnson image? Here's the president's image, right? And I got these projection values down. Now, suppose I want to see which image in my training database most looks like this image that I'm sending across. What I do is I have all the images in the training database, and I get their projections, right? And so there's the mean plus 999 projections. But we're only going to use, say, the first 100 again if we're doing discrimination. So I take this thing, project them down, get these projection values. So I get, say, the first 100 of them. And I compare those 100 projection values to the projection values of these 2,000 images I have in here. So I have 100 images of the president. I have 100 images of the asset director, but I have 20 different people. And I'm comparing the projection values to, I can do the nearest neighbor type of thing with the projection values. I just do a Euclidean distance of this image's projection values versus all these guys' projection values. I see which one's closest, and I say that is the closest image, and it's that person is the president that I'm seeing in this image. Or if I'm saying over, when I say Shirley, if I'm saying over Shirley's image, even with her Lone Ranger mask on, the projection values for her are going to much more match her images than anybody else, even when she's wearing the Lone Ranger mask. So I can do recognition this way as well. Okay, so that's really simple. So back when I was making this work, when I was doing this with Sandy Penland, my advisor, face recognition was a really hard thing to do because everybody's measuring features like eye distance and nose length and this sort of stuff. But here was a really trivial way to take lots of images, train up a system, and do a really large scale face recognizer. And so one of the cool things was that there was this competition called Ferret, if I remember right, in the early days. I think the FBI helped put together to test face recognition systems, and they put 1,000 faces in it. And that was a big deal back then. Everybody was doing 100 faces max. Mostly like 20 faces. And here we were seeing on a technique that could handle thousands and thousands of faces just fine. Could do it in real time, right? Because all we're doing is some projections and some Euclidean distances, and that's it. So we knew we could handle it, and we entered the competition. And I think we were the only people to actually complete the competition because we're the only people who had a method that could handle that many faces. And we did a really good job. I believe we won the competition. And this technique still exists. My advisor really had a thing about the privacy issues of having this technique back in the 1990s. So he had me as an undergrad write code for the technique for every platform out there. It ran on the DEC 5000s, on the IBM platforms. Linux didn't exist yet. On Sun, everything we could get a hold of, we could test. We actually made the code for. If you still go to whitechapel.media.mit.edu, I believe if you look at eigenfaces, you'll still find my code, which was written in KNRC. So it should probably still run using GCC or any other compiler if you get and try it out. However, these days, you get the same eigenface code using a couple lines of MATLAB. I'm not kidding. The main code's like 3 lines. The whole thing might be 15 lines. These days, eigenfaces is really easy to do. But I want you to notice something here. I just showed you how you can send data up to the moon using this very slow connection, using very few data points. I also showed you how you can actually do recognition by using the same projection values and doing clean distance between the faces in your database. But that may not be the best way of doing things. The top eigenvectors best represent the variance of the data. They don't necessarily provide you the best discrimination. So let's take a look at this. Suppose I was going to choose a dimension for best separating the red class from the blue class here. So here's all my, so everybody can see this better. I'm seeing it on the screen. It's kind of hard to see. But these are all my red dots. Right, and these are all my blue dots. These are all my, this is Shirley, the NASA director, versus President Johnson. Right, and I'm trying to separate these two faces. First of all, one of the things I want you to realize is that suppose I put something down, suppose I project something down these eigenfaces that wasn't a face. It would be so far out of this sort of face space, it'd be very easy to recognize as not a face. So I can actually set up a camera and just keep on taking every image and say, is this a face, is this a face, is this a face, and see how far away it is from sort of the mean of face space or anything else in here. And so it's very easy to say, is this a face or not? And that was actually quite a big deal back then. But then let's talk about separating out President Johnson from Shirley, the NASA director. Well, the first, excuse me, I was doing an experiment earlier, which has me a little hoarse. Okay, so the first eigenvector, if I project my classes onto the first eigenvector, it's going to look something like this, right? And that's not very separable. Right, it's like the same, it's pretty much the same Gaussian in that dimension. But if I project, let's see, let's place here to this. We're going to get rid of Shirley down here. And we're going to project onto the minor axis down here just for convenience. If I look at that, I get these much more separable classes. And so it'd be great if I could reorder my eigenvectors in terms of maximum discriminality instead of maximum representation. And that technique is something called linear discriminant analysis. Or sometimes people call it Fisher faces when you talk about face recognition. So while Sandy and Matthew and I spent a lot of time trying out eigenvectors and eigenfaces, I think Tommaso Poggio actually proposed linear discriminant analysis instead and showed that it is better. You do principal component analysis first, and then you take your training set and say, which of these dimensions are most discriminative? Then I use those to actually separate my classes. And so I reorder them, and I say that I'll take the first 20 or first 100 of those 100 eigenvectors, or 999 plus the mean, and I'm going to use those to discriminate. Okay, so again, when I was doing eigenfaces, what we're looking at seeing which vectors are the best for discrimination, I said around the eigenvectors between 20 and 60 were best. So there's 40 eigenvectors between the 20th and the 60th one that seem really good at discrimination. But what Poggio did is said, hey, look, we can automatically figure out which ones are best for discrimination and just use those. We're going to select those ahead of time based on our training set, do k-fold cross-validation. You guys all know that by now. And I'm going to select those and use those for discrimination. Wow. So this technique is still really, really powerful. Today, one of my PhD students, in the past, Zahor, one of my PhD students, did this for sign language recognition. So we were actually trying to work with young deaf students, and we're looking at both, the hand motion, but when I'm doing things like care, right? This is a sort of continuing care. Not only is the hand motion important, but the hand shape is too. Or if I'm saying, blue versus green, hand shape is really important. It's the same motion, the same location. I got to distinguish between these things. So what I do is I find the hand using computer vision. I put a bounding box around it. Just draw a little box around it. So if it's this or this, I'm going to do the same size box actually, and then I'm going to do principal component analysis of it. Get these reference images, these eigenhands, and I'm going to put projection values down. And using the same linear discriminant analysis, we're going to actually take the top, say, 20 projections of say this small image of my hand, and I'm going to use that to encode the shape of the hand. And so along with the X and Y and delta X and Y and sort of the bounding ellipse of the hand, I'm also sending the projection values in off the linear discriminant analysis for the hand shape based off every other hand shape in my database. And this works extremely well. You can actually do real sign language recognition this way. And matter of fact, we deployed our sign language recognition system as part of a game to help young deaf children acquire language skills. And so we actually used this thing for real in a real deaf school and actually showed that the system was good enough. It recognized the sign language good enough that the students actually played the game and significantly improved their memory skills while playing this game. Again, all it was basically looking at the hand motion and the shape of the hand using, I think we actually used PCA originally, but we should have used LDA. It worked. And that's one of the things also is that the difference between PCA and LDA in most situations is not that great. It's you might get 2% improvement often. Sometimes you get more than that. But LDA is actually the right way to do it. PCA works almost as well most of the time. Okay, so I know that was a lot to take in, but whenever you're doing, let me give you one other example for this. Suppose I am looking for, say, gesture recognition using a smartwatch. Well, it's got its own basis of X, Y, and Z. You don't know how that sensor is embedded in that watch. You don't know which angle it's at. But one of the things you can do is collect lots of data from that wristwatch and do a principal component analysis on it, and you figure out which dimension has the most variance in. And that's basically the tilt sensor. An accelerometer in a watch basically is a tilt sensor because you have acceleration due to gravity. And basically the tilt relative to gravity is going to be your biggest variation. And that's also going to depend on how the person wears the watch, where they wear their watch, what sort of motions they're making. But you can do PCA to figure out which dimension is going to be most important. And you also use that for calibration for that person. And so you can make it, so you can try to calibrate across people. So PCA is often very useful for both dimensionality reduction, to help figure out what features you really care about, but also can help be used for calibration between users or across sensors. You can imagine that, if I have one smartwatch, suppose I'm doing Android watches, one smartwatch has a sensor mounted this way, another one has it mounted this way, right? You basically want to have the same dimension every time. Do PCA, look at the areas of most variance, and then you can actually use that for your recognition. Okay, so that's generated so we have a lot of comments here. Eigen images with faces in ML, they create very interesting images. Yes, I didn't know they're doing eigen faces these days in ML. That's very good. I don't know if that was Charles's classes or whose class. I used to do a whole lot more machine learning stuff in AI, but now I just give you a taste of it, assuming that you're going to do machine learning at some point if you want to continue doing it. There's a you posted an eigenface on Piazza. That's cool. I gotta reload. Let's see which one you did. Oh yeah, there you go. So Christopher has given us an example of all the eigenfaces out there on the Piazza thread. So that looks like that might be like 16 faces or so. No, that one's probably 20, 24. 24, 25 images, I bet, would be the size of that data set. And they're not quite aligned as well as I would like normally, but it kind of gives you an idea of what's going on with eigenfaces. All right. Computer vision contains an assignment related to PCA working with eigenfaces. Great. It's a technique that you'll see in the literature a lot. Chris says, wasn't there when he did it? Problem set 6. So you guys do PCA eigenfaces first, and then you do Viola-Jones. Yeah, Viola-Jones is the template cascade where you're trying to be you're trying to reject, you figure out if there's a face there or not, and reject as quickly as possible. CV2 hard transforms might be doing something similar. Now I'm thinking about the hard transforms are mostly what you're doing with hard is looking for the features that can tell you whether or not it's a face quickly or a particular face quickly. And that's generally optimized for just quick rejection. So you can actually put these algorithms into your point and shoot cameras for finding faces or finding people who are smiling. Basically, it looks at every image and quickly rejects the image if there's no face in it. If it looks like a face, like you're looking at a dog instead of a face, it will keep on looking more and more carefully until it can reject that face. So let's see here. So I got no more questions there. I'm glad you guys are seeing this in other classes. Let me reload Piazza and make sure there's no questions there. Nope. Okay. Do I have a slider here? Yes. Okay, so Chris says, the sign language stuff is interesting to me since my sister is a speech pathologist. Yep. Considering my own battles, having a learning disability in reading and writing. Yeah. So it turns out I have a very hard time learning other spoken languages. I've tried German. I've even lived in Germany for a while. Couldn't really do it. Tried Spanish in high school. Couldn't really do it. But sign language, I learned more quickly. That was really poor grammar and sign, but you get the idea. One of the things that you should talk to your sister about is that it turns out there's been a lot of studies now that show that there is that teaching your child sign language, whether or not they're hearing, actually is one of the fastest ways to encourage language acquisition skills. It turns out that the larynx, when you're born, is actually in your chest. And it allows you to both drink milk while breathing at the same time for the first 6 months of life. It only really gets to the point, it only gets separated from the rest of your throat about sufficiently so you can start talking about around 12 months. So it starts separating out at 6, really gets separated at 12, and you start doing consonants. So it means that infants don't have the apparatus to speak spoken language until they're about 12 months or so. But they can sign. They'll start replying to you at 6 months. And it turns out that learning to generate language is what actually causes you to learn short-term memory. And so all these baby sign advocates, what they're actually doing by encouraging you to teach sign language to your child is basically allowing you to teach short-term memory to your child much earlier. And that, of course, applies to any language or reading or writing or learning in general. And so by teaching your hearing or your deaf kids sign language, you're actually encouraging learning in general because you're encouraging short-term memory. So there used to be a myth that if you taught your kids sign language, you never speak English. It turns out to be completely wrong. It turns out teaching your kids sign language is the best thing you can do for them as far as encouraging language skills, because it encourages that short-term memory. And the baby sign people, cite that they get IQ improvements up to age of 5 or so, which I now kind of believe because of the short-term memory thing. So anyways, I'm a big advocate of teaching your infant sign language. Okay, I was doing research, came across the ROC curve. Yep, receiver operator characteristic curve to improve threshold value for splitting. Yep. So ROC, this is basically also sometimes you think of as a precision recall curve. Basically, it's saying so of the items in the database, how sensitive am I to actually picking out the right, detecting when there is an appropriate action or item in the database. And precision is saying, when I say there's something in there, how often am I right? And the ROC curve kind of captures that. And it comes from radar and signal stuff, basically from World War II. We were trying to say, is the enemy warplane coming in? How many times do I false positive versus false negative, that sort of thing. And so ROC and the Bayesian information criteria and all this type of stuff is related to each other. And so you can actually use this to help tune your system. It's all also related to minimum description length. All this stuff is related to each other. You can use it to test the system and tune the system. All right. Thank you, Arsh, for bringing up that idea. There was something else back here earlier on. People were talking about discrete cosine transform. Okay. Well, I'm in the middle of an experiment, folks. So if there's nothing else, will you be doing an exam review as you have in previous semesters? No. What the TAs have been doing recently is they actually they actually go through each question on Piazza separately in detail. I believe they've already done that, showing what answers they would accept. So I think the TAs have already started talking about the questions and answers on Piazza. And so they determined the TAs believe that is a more efficient and effective way of doing this stuff. It's also, each TA who made you can now figure out which TA did each question by who's posting what, so you know who to blame. Be nice. Look at Piazza for the exam review. I assume you're talking about post-exam review, not pre-exam review. If people are really interested, I might do a pre-exam review too when we get to the final. Just so you guys kind of, maybe we'll take an old exam and go through it. Most of those will be challenge questions already, so you'll already seen most of them. It still might be useful for folks to see, be able to ask questions interactively. All right. Okay, so let me look at Piazza again, make sure there's nothing else there. And if nothing else, I am going to go back to doing some passive haptic rehab work. We are trying to enable, to actually encourage rehabilitation of swallowing reflex post radiation exposure for people who are being treated for cancer. And so this involves lots of putting vibrators on our vibrating motors on our necks and seeing if we can actually see the vibration. Love being busy right now trying to mess around with biology. Okay, so I will catch you guys next time. And I will see you later. Thanks much, folks. Oops.